Have you ever wondered just how ridiculously massive the biggest known sun in the cosmos truly is? Well, prepare to have your mind blown. Imagine dragging this cosmic behemoth back to our neck of the woods and dropping it right in the center of our neighborhood. Its blazing exterior wouldn't just swallow our local star. It would expand all the way out past the rings of Saturn. Think about that. Mercury, Venus, our home world, the red dust of Mars, and even the gas giant Jupiter. Every single one of them would be completely incinerated, buried deep within the scorching plasma of this absolute monster. In this episode, we will unravel the story of a celestial giant fighting a losing battle against its own blinding radiation, pushing right up against the absolute physical boundaries of the universe, and forcing scientists to completely rewrite the rulebook on how huge a sun can actually grow. But before we dive into the cosmic abyss, if uncovering the hidden secrets of the galaxy sparks your imagination, please hit those like and subscribe buttons. That quick click does wonders for pushing our interstellar journey out to fellow space enthusiasts. All right, let us warp back to 1990. An astrophysicist named Charles Bruce Stephenson was meticulously mapping the heavens, hunting for colossal stellar nurseries concealed behind thick veils of galactic soot. His focus was locked onto Scutum, a rather dim grouping of stars in the southern hemisphere, perfectly aligned with the thickest part of our home galaxy. That specific patch of space is an absolute traffic jam of cosmic debris, floating nebulas, and countless suns. It looks stunningly brilliant and packed together from afar, yet it acts like a dense fog bank, hiding its deepest secrets. Staring through that cosmic smog with regular telescopes is practically impossible. However, by shifting to thermal imaging, which easily slices right through that thick interstellar muck unlike normal light rays, Stephenson stumbled upon a group of suns located 19,000 light-years away. And this was no ordinary collection. It held some of the heaviest, most blindingly radiant objects ever documented in human history. We are talking about massive crimson titans and searing hot sapphire behemoths, furious engines of creation blasting out hundreds of thousands of times the power of our own sun, officially earning the name Stephenson 2. For decades following its discovery, it was just another footnote in science textbooks. A neat but mostly forgotten stellar nursery lost in a sea of galactic data. Yet, as our thermal technology leveled up throughout the 1990s and the 2000s, bringing absolute marvels like the Spitzer and Herschel orbital observatories into the fold, researchers took a second, much closer look at that specific cluster and noticed something absolutely mind-bending. A single point of light was stealing the entire show. Its thermal signature was off the charts, glowing with a ferocity that made zero sense for your standard crimson giant. The radiation levels were so intense that scientists initially assumed it had to be a foreground object, though the odds of that were incredibly slim, leaving only one other terrifying possibility. Its physical size was simply incomprehensible. They officially labeled this anomaly Stephenson 218, marking its place as the 18th entry on the roster. At that exact moment, not a single soul grasped that they had just pinpointed the undisputed heavyweight champion of the cosmos. The true gravity of the situation only dawned on them after grueling months of crunching the raw data. Which brings us to a massive scientific roadblock. How exactly do you figure out the waistline of a fireball sitting 19,000 light-years in the distance? Sending a robotic rover is out of the question, and snapping a crisp photograph is physically impossible. All you have to work with are tiny particles of radiation that have been soaring across the dark void for 19 millennia. This is illumination that initially shot out into the universe back when our ancestors were still roaming the plains with spears, way before the very first stones of the Great Pyramids were ever laid down. Predating the invention of written language, farming, and modern society itself. Have you ever wondered how we can possibly know the secrets of a stellar giant we can't even visit? When those incredibly ancient particles of light finally hit our observatory lenses, we have to piece together an entire cosmic puzzle. We figure out how hot it burns, how intensely it glows in the dark, how unimaginably huge it is, how much it weighs, and what exactly it is made of. All by just looking at a beam of light. Figuring out its apparent glow is our opening move, and honestly, it is the simplest part of the job. You just aim your massive mirror at that specific patch of the sky, gather those traveling waves, and calculate exactly how much raw energy washes over your digital sensors. Astronomers call this the apparent magnitude, which is basically just a fancy way of expressing how shiny the object looks from our vantage point here on Earth. Now, if you step outside to look for Stephenson 218, you are going to be disappointed. It looks incredibly dim, completely invisible to human eyes alone. Even if you grab a decent backyard scope, it completely vanishes into a massive sea of thousands of glowing neighbors in that packed galactic city. But when we switch to heat-sensing infrared gear, the story completely flips. It suddenly blazes like a beacon, drastically outshining its normal visible footprint, which is exactly what you would expect from a relatively chilled-out celestial giant. You see, suns with lower surface temperatures dump the vast majority of their power out as invisible heat waves, rather than colors we can actually see with our eyes. Once we have the brightness down, we have to figure out the exact mileage between us and the target. Just knowing how much light hits our lens is a trick question. Imagine a flashlight right in your face versus a massive lighthouse miles away. They might look exactly the same to you in the dark. To uncover its true underlying power, you absolutely have to nail down its exact distance from our solar system. A crucial measurement scientists refer to as its true luminosity. When a target is sitting relatively close by, say within a couple thousand light years, we rely on a brilliant trick called parallax. Imagine closing one eye, then the other, while looking at your finger. In the same way, as our planet races around the sun, the stars closest to us seem to wobble back and forth compared to the deeply frozen, motionless backdrop of the wider universe. Tracking that microscopic wiggle lets us use high school geometry to pinpoint their exact location in the cosmos. The catch? That cool geometry trick completely falls apart when things get insanely far away. At 19,000 light-years deep into the abyss, that visual wobble becomes essentially zero. Not even our most advanced orbital cameras can spot the shift, forcing space detectives to get a lot more creative. Fortunately, Stephenson 218 hangs out in a massive stellar group. By analyzing the entire neighborhood of stars all at once, and cross-checking the traits of those companion suns against our mathematical blueprints of stellar evolution, researchers can effectively narrow down the gap and lock in a solid range. Of course, every measuring tool has its unique quirks, giving us a slightly different cosmic yardstick, which is why the exact mileage for Stephenson 2 is debated, falling somewhere in the ballpark of 17,000 to 20,000 light-years away. Let us roll with 19,000 as our gold standard. Combining that sheer distance with its apparent glow unlocks the ultimate prize, its true cosmic wattage. We finally get to ask the big question. How much raw fire is this monster actually blasting into the void every single heartbeat? When researchers crunched the numbers, the final answer was completely mind-blowing. Stephenson 218 burns with a ferocity roughly 440,000 times stronger than our own familiar sun. Let that sink in. Every tick of the clock, this titan radiates 440,000 times the heat and light of our entire solar system's engine. It is a level of sheer violence and energy that the human brain can barely process. Yet, blinding power does not automatically equal immense physical bulk. You could have a tiny, furiously boiling dwarf star that shines like a diamond. Or you could have an unbelievably swollen, lukewarm giant putting out the exact same amount of total light. To measure its true physical waistline, we have to take its temperature. Enter spectroscopy, the ultimate fingerprinting tool of the universe. By fracturing the incoming beam of starlight into a beautiful rainbow and hunting for missing bands of color, scientists can read the exact thermal output of its outer shell. You see, the hotter the fire, the vastly different the chemical barcodes it leaves behind. Boiling blue titans leave completely different shadow patterns in their light compared to their chilly red cousins. When scientists unspooled the colorful barcode of Stephenson 218, the truth was instantly undeniable. This beast is practically shivering by stellar standards. It is remarkably icy for a giant. The outer atmosphere registers at merely 3,600 Kelvin, which translates to roughly 6,000 degrees Fahrenheit. Sure, that sounds like a blazing inferno to you and me, easily enough to melt steel right here on Earth. But in the realm of deep space titans, it is practically a gentle winter breeze. Have you ever wondered just how scorching our local star really is? Well, the outer layer of our own sun burns at roughly 5,770 Kelvin, which is well over 10,000 degrees Fahrenheit. In stark contrast, a cosmic titan named Stephenson 218 is actually much colder, giving it a deep, fiery crimson hue. In the cosmic color palette, chillingly low temperatures produce scarlet hues, while the most blistering stellar objects shine with a brilliant blue or pure white glare. By breaking apart the light coming from this giant, astronomers even spotted intact chemical compounds drifting through its outer gas layers. We are talking about compounds like titanium oxide, drifting water vapor, and even carbon monoxide. These fragile chemical structures can only survive in environments that are comparatively chilly. Any extreme heat would instantly shred them into basic atoms, proving definitively that we are looking at an unbelievably massive but frigid hypergiant. That brings us to the ultimate mathematical puzzle. Once scientists figure out the absolute brightness, or the sheer amount of light pouring out of a stellar body, and pair that with its outer heat level, they can deduce its exact physical dimensions. This magic trick relies on something physicists call the Stefan-Boltzmann principle, which dictates that a star's total power output hinges on just two key factors. First, the intensity of the heat radiating from its skin. Blazing shells naturally blast out way more power per square inch. And second, the sheer expanse of that outer area. Therefore, for a dim, chilly star to shine incredibly bright from millions of light years away, it has to be impossibly wide to push out all that energy. When the scientific community finally ran the math on Stephenson 218, the final figures completely blew their minds. It turns out this monster is anywhere from 2,000 to 2,400 times wider than our home star. And to really grasp what that means, consider that our sun's halfway point is roughly 433,000 miles deep. Scale that up by a factor of 2,000, and you are staring at a jaw-dropping measurement of nearly 930 million miles. Keep in mind, that is only the trip from its very core straight to the outer edge. If you wanted to travel straight across the entire beast, you would cover an astonishing 1,860,000,000 miles. Without a doubt, Stephenson 218 holds the crown for the most colossal celestial sphere we have ever found in the cosmos. So, with the mystery of its discovery and colossal measurements solved, we must ask ourselves, what does a span of 930 million miles actually look like? Without a familiar comparison, a scale that massive simply breaks the human brain. Let us paint a mental picture together. Imagine a magical scenario where we pluck our sun right out of the sky and drop Stephenson 218 in its place, leaving every single planet exactly where it is today. The aftermath would be completely terrifying. The beating heart of this red monster would be anchored at the exact center of our solar neighborhood. However, instead of stopping at a cute 433,000 miles away, the fiery walls of this hypergiant would blast outward for roughly 10 astronomical units in every single direction. To clarify, a single astronomical unit represents the gap between humanity's homeworld and the sun, a cool 93 million miles. This cosmic beast would stretch its blazing edge a full 10 times farther than that. Poor little Mercury. Cruising at just 0.4 astronomical units away, it would be instantly swallowed up, vaporized in the deepest layers of plasma. The toxic world of Venus, floating at 0.7 units, erased without a trace. And what about our beautiful Earth at 1 full unit? Our entire home would be swallowed whole, not even close to the giant's outer rim. We would be utterly buried inside a suffocating ocean of stellar gas. The red dirt of Mars at 1.5 units, and even the millions of floating rocks in the asteroid belt situated between 2 and 3 units would all vanish into the beast. Think about mighty Jupiter, the undisputed heavyweight champion of our planets, which hangs out at 5.2 astronomical units. Even this majestic gas giant would be totally eclipsed, melting inside an endless sea of glowing crimson. Finally, we reach Saturn, the crown jewel of rings, drifting far out at 9.5 astronomical units. Unbelievably, the sheer bulk of Stephenson 218 pushes even further into the dark void than Saturn's path. Picture yourself hovering near Saturn's icy rings, gazing into the heavens above. Instead of a twinkling dot piercing the cosmic dark, you would be face to face with an endless, ominous wall of crimson plasma, devouring your entire field of view and radiating heat like a universe-sized bonfire. You would find yourself swallowed whole by this stellar behemoth. In fact, only Uranus, sitting 19 astronomical units away, and Neptune, out at 30, would manage to trace their paths beyond its fiery edge. As for the Kuiper Belt, that frozen wasteland of debris lingering past Neptune, it would sit safely tucked away in the freezing void, far from the reach of this galactic monster. Let us take a moment to wrap our heads around its sheer physical space. You see, the overall capacity of a sphere grows exponentially, cubing itself against its radius. Since Stephenson 218 stretches out roughly 2,000 times wider than our own sun, we have to multiply that 2,000 by itself 3 times. 2,000 times 2,000 times 2,000 gives us an absolutely mind-bending figure of around 10 billion. Imagine scooping up our sun and tossing 10 billion exact copies of it into the belly of Stephenson 218. We are not talking about 10 suns or 100 or even a million. We mean 10 billion. Picture our local star, shrunk down to the size of a standard yellow tennis ball. On that same scale, this colossal red giant would swell into a massive globe spanning 1,000 feet, standing just about as tall as a towering 100-story skyscraper. Or think of our sun as a tiny glass marble, making this hypergiant bigger than your entire house. These proportions are honestly so staggering that our minds simply struggle to comprehend them. Yet the mystery deepens with a truly bizarre twist. Even though it eats up 10 billion times more space, Stephenson 218 barely holds 12 to 16 times the actual mass of our sun. What kind of cosmic trickery is at play here? It all boils down to one simple concept: density. This particular behemoth belongs to a colossal stellar family known as Stephenson 2, which first caught the eye of astronomer Charles Bruce Stephenson back in 1990. Tucked away deep within the galactic plane, this entire grouping is heavily buried beneath thick, swirling clouds of cosmic dust and gas. Because it hides behind such a chaotic veil, getting a clear look is an absolute nightmare for scientists, as all that debris greedily swallows up and scrambles any incoming light, especially the kind our eyes can actually see. To pierce through this murky fog, those initial pioneering studies relied entirely on infrared observatories, whose specialized lenses can cut right through cosmic smog far better than traditional optical equipment ever could. By peering into the thermal spectrum, researchers uncovered that the Stephenson 2 neighborhood was secretly hosting some of the heaviest and most blindingly bright stellar bodies in the known universe. Yet, even among a crowd of absolute titans, one specific orb commanded everyone's attention. Stephenson 218 displayed highly unusual quirks, hinting at proportions so monstrous that it made the surrounding hypergiants look modest. Trying to figure out the exact physical dimensions of a blazing sphere located that unimaginably far away means scientists have to get incredibly creative with their math. It is not like checking out the moon, where you can just aim a backyard scope and calculate the distance from edge to edge. Floating a staggering 19,000 light-years out into the blackness, the absolute biggest objects in existence look like tiny, singular pixels of brightness. To solve this puzzle, astrophysicists weave together a clever mix of investigative tools. The first piece of the puzzle is capturing its radiance, specifically its apparent magnitude, a fancy term for exactly how dazzling that speck looks to us standing here on Earth. Following that, they crunched the numbers to map out the sheer mileage separating us, pulling from a toolkit of different observational tricks. A common shortcut involves analyzing the behavior of its neighboring sister stars within the same cluster. Once you nail down how bright it looks and how far away it sits, you unlock its true luminosity. This tells you the absolute maximum wattage this stellar engine is blasting into the void every single tick of the clock. It turns out, Stephenson 218 shines with a fierce intensity 440,000 times stronger than our own local star, which translates to it violently erupting 440,000 times more raw power per heartbeat than the sun that warms our faces. Moving on to the next clue. Researchers take the star's literal temperature by ripping its light apart into a rainbow and studying the specific spectrum of colors left behind. Because cosmic fires burn in highly predictable ways, specific heat levels will always stamp a unique barcode onto that colorful light spread. The outer skin of Stephenson 218 simmers at around 3,600 degrees Kelvin, pushing the thermometer up to roughly 6,000 degrees Fahrenheit. While that sounds like an absolute inferno to you and me, in the realm of celestial heavyweights, it is practically a frosty winter breeze. For comparison, the surface of our home star cooks at 5,770 Kelvin, practically 10,000 degrees Fahrenheit. This massive temperature drop makes Stephenson 218 relatively chilly compared to our sun, causing it to burn with an angry crimson glare instead of a piercing yellowish white. It is a universal rule. The colder the star, the deeper the red, while the ultimate cosmic furnaces always radiate in blistering shades of blue and white. So how do we actually figure out the size of something so impossibly far away? Once astronomers pin down a star's brightness and heat, they rely on a brilliant piece of physics known as the Stefan-Boltzmann law to map out its physical footprint. Think of this rule as a cosmic balancing act that ties together how much light an object pumps out, how hot its surface gets, and its total surface area. If a celestial body is relatively chilly but still blindingly bright, it simply must be gargantuan in size to radiate all that power into the void. When scientists run the numbers for Stephenson 218, the results are staggering. Its radius spans anywhere from 2,000 to 2,400 times that of our own sun. Why the massive ballpark figure? Well, pinpointing. The precise thermal output and sheer brilliance of an object thousands of light years away naturally comes with a bit of blurry math. Yet, even if we assume the absolute lowest end of that scale, we are looking at a celestial behemoth that completely shatters human comprehension. 2,000 solar radii equates to a distance from the core to the edge of roughly 930 million miles, making its total width an astonishing 1,860,000,000 miles across. Push that to the absolute maximum estimate of 2,400 times the sun's girth, and the edge stretches out to roughly 1,120,000,000 miles, giving it a colossal beltline measuring 240 million miles from side to side. Regardless of which measurement is spot on, it easily takes the crown as the most humongous star humanity has ever laid eyes on. Of course, the universe is packed with heavyweight contenders. Cosmic titans like UY Scuti, VV Cephei A, and WOHG 64 have all taken turns wearing the heavyweight championship belt in the past. The truth is, our galactic tape measures are constantly evolving, becoming significantly sharper as next-generation telescopes power up and deliver crystal-clear data to researchers. For a long stretch, UY Scuti was the undisputed king, boasting an estimated size around 1,700 times our Sun. However, recent observations armed with cutting-edge technology drastically shrank that profile down to about 755 solar radii, stripping it of its colossal reputation. As it stands today, Stephenson 218 easily dwarfs the competition based on our most reliable metrics. But the cosmos loves a plot twist, and astrophysics is a field of endless tweaking and tuning. Tomorrow's deep space observatories could very well rewrite the record books once again. Still, we can safely bet our telescopes that Stephenson 218 is an absolute titan among the cosmic giants, and quite possibly the unrivaled champion of the galaxy. But that leads us to a fascinating, mind-bending question. What exactly stops a blazing sun from growing indefinitely? Is there a cosmic speed limit for size? Logic might suggest that if you just keep piling on enough space dust and gas, you would inevitably sculpt an infinitely expanding megastar. But the reality of stellar physics completely rejects that idea. The universe enforces strict structural boundaries, dictated entirely by the unyielding, fundamental forces of nature. At the heart of every glowing sun is a brutal, non-stop nuclear engine powering the light we see. Deep inside, violent collisions smash hydrogen atoms into helium, unleashing waves of pure explosive energy. That ferocious blast creates a massive outward thrust, fighting desperately against the crushing, suffocating weight of the star's own gravity. Essentially, a living sun is an eternal, high-stakes tug-of-war between two unstoppable phenomena. Gravity wants nothing more than to crush the entire sphere into a tiny, dense speck. Meanwhile, the roaring atomic furnace pushes outward, and when these two combatants lock into a perfect stalemate, you get a stable, shining, celestial body. However, the truly gargantuan spheres, those packing 8 to 10 times the sheer bulk of our local sun, live like absolute rock stars, blazing hot and burning out extremely young. They guzzle down their atomic fuel reserves at a terrifying, unsustainable pace. The heavier and bulkier the celestial body, the more violently its core must cook in order to summon the immense outward force required to avoid collapsing under its own massive weight. Cranking the thermostat up this high puts the atomic reactions into extreme overdrive. Instead of sipping on their hydrogen for billions of years like our sun does, these heavyweights torch their entire supply in a mere few million years. Once the primary fuel tank hits empty, absolute panic sets in, forcing the core to start crushing helium into carbon. And as soon as that runs dry, it desperately welds that carbon into even denser materials. This frantic atomic alchemy climbs the periodic ladder, forging things like oxygen, neon, magnesium, and silicon until it hits a deadly brick wall: iron. With every step down this desperate path, the resulting power drop is severe, and the countdown to the star's ultimate destruction accelerates dramatically. Have you ever wondered what happens when a colossal sun runs out of fuel? A giant cosmic furnace might burn through its primary hydrogen supply for millions of years, then spend a few thousand more cooking up helium, followed by a few centuries melting down carbon until it reaches a desperate final sprint, forging silicon into iron in a mere handful of days. But iron is the ultimate cosmic dead end. Forcing iron atoms together doesn't give off a single drop of power. Instead, it acts like a giant sponge, draining the star's vitality until the internal engine simply switches off. Without that outward push of radiation, the crushing grip of gravity takes absolute control. In less than a heartbeat, the center violently implodes, unleashing the blinding fury of a supernova blast. So why can't these celestial beasts just keep growing forever? That is where stellar physics gets truly fascinating. When an aging sun switches to burning heavier elements, it transforms, ballooning outward into the void. Its deep interior shrinks and gets incredibly hot, while its outermost atmospheric layers puff out and drastically chill. That expanding jacket of gas creates what we call red supergiants, or the phenomenally rare beasts known as hypergiants. Enter Stephenson 218, a genuine hypergiant gasping its final cosmic breaths. It has puffed up to mind-boggling proportions, stretching out like a cosmic balloon as its dying heart tightens up. Yet the universe enforces a strict physical boundary on how big a sun can actually stretch. Astrophysicists call this ultimate ceiling the Eddington limit. Think of it as a breaking point, where the blinding glare pushing outward from the core overpowers gravity's inward pull, literally shredding the star to pieces. You see, every beam of starlight packs a tiny physical punch. As gazillions of light particles race away from the center, they crash into the gases hovering at the star's edge, shoving them outward. For your average run-of-the-mill sun, this gentle push is barely noticeable against the massive anchor of gravity. But crank up the brightness to extreme levels, and that light pressure turns into a raging hurricane. Inside behemoths like Stephenson 218, the outward force of that light is absolutely staggering. This monster shines 440,000 times brighter than our own solar system's star, meaning a relentless tsunami of photons is constantly battering its outer shell. If it were to crank up the dial even just a fraction more, the light would completely overwhelm gravity's grip. The star's entire outer skin would be blasted straight into the freezing void of deep space. In fact, this violent unraveling is exactly the fate that meets the heaviest stars in the cosmos. They constantly bleed their own gas into the galaxy, driven away by incredibly aggressive stellar gales. Stephenson 218 is almost definitely shedding its mass this exact same way. Its colossal outer atmosphere is slowly being sandblasted away by its very own blinding glare. Down the line, this giant will shed so much weight that it simply won't have the bulk to keep up its bloated appearance. Then the final act begins. A catastrophic cave-in, a blazing supernova, and the birth of a super-dense neutron star, or a pitch-black singularity. Ultimately, the ceiling on stellar size is not just a simple matter of dumping more gas onto the fire. It is a delicate, razor-thin balancing act between the inward crush of gravity, the outward blast of starlight, and exactly how far along the star is in its life cycle. Stephenson 218 is teetering right on that edge. If it grew even an inch, it would rip itself apart. But what if we could actually travel there? Imagine taking a cosmic road trip to witness this titan up close. Picture yourself peering out the viewport of a futuristic ship, cruising toward Stephenson 218 from millions of miles away. Forget about a twinkling little dot in the night sky. This behemoth would swallow your entire window. It would appear as an endless burning horizon stretching across the very fabric of space. Drifting closer, you would notice a deep, rusty hue washing over your surroundings. Because its outer layers are relatively chilly for a star, it burns with a hazy crimson-orange glow instead of a piercing sapphire or brilliant white. Strangely enough, its actual surface would look a bit muddy compared to our own blazing sun. Even though it cranks out 440,000 times more total energy, all that brilliance is stretched so thin across its colossal girth that any single patch of its skin is surprisingly muted. If you could magically hover on a viewing deck right above that rolling sea of red plasma and gaze out into the wild unknown, have you ever wondered what it would look like up close? Surprisingly, your surroundings wouldn't actually dazzle you with an overpowering glare. Instead, picture the fading, fiery embers of a dying campfire. That's exactly how this giant would simmer. You might even be able to gaze right at its exterior without immediately scorching your retinas. Make no mistake though, the invisible waves of infrared energy would extinguish your life in a heartbeat. Meaning the true threat lurking here isn't something you can visually perceive. The real killer is the ferocious heat. And while the outer crust sits around a relatively modest 3,600 degrees Kelvin, the sheer volume of thermal energy pouring off this monster would instantly incinerate any object foolish enough to approach. Imagine hovering exactly where our home planet sits relative to our sun, but plunging that same distance deep inside this behemoth. If by some miracle you were shielded from immediate destruction within this stellar beast's colossal gaseous layers, the thermometer would easily register multiple thousands of degrees. Every single atom exists as superheated plasma, making it completely impossible for anything solid to hold its shape. Diving deeper toward the heart of the anomaly, that inferno aggressively ramps up into the millions. Deep within the central engine of Stephenson 218, where atoms are violently smashed together, the environment flares up to a mind-bending several 100 million degrees Kelvin. Under such extreme conditions, normal materials completely shatter apart into naked atomic cores and wandering electrons. You'd be crushed by a weight millions of times heavier than the air pushing down on us right here on Earth. Absolutely nothing resembling a tangible, solid structure could ever survive such hellish, crushing forces. It becomes an alien domain, ruled entirely by raw, untamed energy and the most basic building blocks of reality. But do you know what the most fascinating secret about Stephenson 218 actually is? It's how incredibly fleeting its life truly is. Cosmic giants of this magnitude are exceptionally scarce, not only across the vastness of galaxies, but also throughout the timeline of history. Think about our own familiar sun, which gets to enjoy a comfortable existence lasting roughly 10 billion years. Sitting at approximately 4.6 billion years of age right now, our local star is just coasting peacefully through middle age. It gets to happily burn through its hydrogen reserves for another 5 billion years before finally exhausting its tank and bloating up into a massive red sphere. Yet when we shift our gaze back to the mighty Stephenson 218, its entire grand performance will be over in a mere 20 million years, perhaps even sooner. There is a very real chance this Titan has already blown itself to pieces, but we remain completely oblivious because the visual evidence is still racing across the void to reach our telescopes. Keep in mind, this colossal inferno sits a staggering 19,000 light-years away from our cosmic neighborhood. The image painting our night sky right now is just an ancient snapshot of how the beast appeared 19,000 years in the past. Had it violently detonated 10,000 years ago, humanity wouldn't witness the fireworks for another 9,000 years. This mind-bending delay in information is one of the most magical and confusing quirks of observing deep space phenomena. Every time you tilt your head up at the night sky, you are literally peering into a time machine. Whenever Stephenson 218 inevitably meets its doom, the resulting cataclysm is going to be an absolute masterpiece of destruction. Massive stellar titans of this class generally conclude their dramatic stories as breathtaking supernovae, or perhaps even as hypernovae, which are essentially standard star deaths pumped full of cosmic adrenaline. These souped-up explosions unleash a level of sheer power that makes a regular stellar blast look like a tiny firecracker, potentially triggering a devastating gamma-ray burst, the absolute most violent phenomenon in all of existence. second only to the dawn of the universe itself. In just a handful of ticking seconds, these bursts violently eject more power than our dependable local star could ever dream of generating across its entire 10 billion year history. Should Stephenson 218 fire off one of these cosmic death rays straight down the barrel toward our solar system upon its demise, we would actually be able to spot the flash from our backyards. Despite that massive 19,000 light-year gap, you'd see a blindingly brilliant dot suddenly ignite right inside the Scutum constellation, glowing so fiercely that you might even catch it shining through the bright blue daylight for a brief window of time. But you can take a deep breath because there's absolutely no reason to panic. Across a gulf of 19,000 light-years, all that deadly radiation would get scattered and swallowed up by cosmic dust long before it could ever threaten our atmosphere. Our beautiful blue marble would remain perfectly out of harm's way, leaving us free to simply enjoy the show. From our safe vantage point, Earth would simply be treated to the most breathtaking cosmic fireworks display imaginable. The stellar wreckage would blast across the cosmos, racing outward at mind-bending velocities that rival the speed of light itself. As this shockwave crashes into nearby interstellar clouds, it will ignite them into a brilliantly shimmering tapestry of cosmic gas. Long after the initial explosion, this luminous ghost would paint the night sky for millennia, before finally whispering away into the dark, while deep inside, the star's ancient heart crushes inward on itself. When we weigh this celestial behemoth, clocking in at roughly 12 to 16 times the heft of our own sun, we find it teetering on a fascinating cosmic edge. It sits perfectly on the razor-thin boundary dividing two incredibly bizarre destinies, becoming an ultra-dense stellar corpse or an inescapable abyss. Those crushed remnants, known as neutron stars, are born when a dying core tips the scales somewhere between 1.4 and 3 times our sun's weight. However, if the crushing gravitational force tips past that crucial threshold, gravity wins the ultimate wrestling match, squeezing the matter entirely out of existence to birth a bottomless, dark void. The final destiny for the colossal Stephenson 218 entirely hinges on how much of its own outer atmosphere it has already blown away into the void. A violent history of shedding material could leave behind just enough guts to forge a spinning stellar remnant. But if it held tightly onto its bulk, an unyielding black hole is inevitable. Regardless of which path it takes, the reign of this monstrous titan will reach its absolute end. All that unfathomable majesty will be reduced to a tiny, intensely compressed shadow of its former self. Have you ever wondered what true scale looks like? Let us line up Stephenson 218 against some other famous stellar heavyweights to truly grasp its mind-boggling proportions. Think of our familiar sun, a completely ordinary yellow dwarf sitting comfortably in the middle of the cosmic bell curve. In reality, the vast majority of our galactic neighbors are quite petite and chilly by comparison, especially the faint little glowing embers we call red dwarfs. These tiny stellar engines are barely heavy enough to spark nuclear fires, yet they account for a staggering 70% of the galactic population. Picture a humble glowing orb spanning a mere 10 to 20% of our sun's width, carrying only 10 to 50% of its total gravitational heft. They are the universe's ultimate underdogs. Small, incredibly faint, and absurdly resilient, hoarding their fuel so efficiently that the smallest among them will keep shining for trillions of years. But swing your gaze over to the opposite end of the spectrum, and you will encounter the terrifyingly majestic realms of the blue superbosses and hyperscale leviathans. These absolute units of the cosmos are blisteringly hot, staggeringly heavy, and shine with a blinding ferocity. Look at Rigel, the brilliant sapphire beacon marking the foot of the Hunter constellation. This blazing giant spans roughly 79 times wider than our local star. Next to our pale yellow dot, it looks like an absolute giant. Yet it shrinks to a mere speck when brought anywhere near Stephenson 218. And then we dive into the domain of the bloated scarlet behemoths, stars that have chilled out while expanding to horrific proportions. Take the legendary Betelgeuse, that unmistakable ruby jewel glowing brightly at the shoulder of Orion, which easily holds the crown as humanity's favorite stellar heavyweight. Because it constantly throbs like a beating heart, its waistline shifts, though astronomers gauge its average span at an incredible 764 times the width of our Sun. The sheer scale is almost beyond human comprehension. Swap it into the center of our solar neighborhood, and its fiery outer edge would easily swallow Mercury, Venus, Earth, and Mars, likely scraping the dusty edges of the asteroid belt. Yet, astonishingly, the gargantuan Stephenson 218 is roughly triple that size. Consider the fiery heart of the Scorpion, Antares. This famous crimson monster puffs out to about 680 solar widths. Then there is the sprawling VV Cephei A, a monstrously bloated celestial body long hailed as a cosmic king, ballooning out to a staggering 1,500 solar widths. Yet even this titan falls short of the champion we are discussing. And we cannot forget UY Scuti, the former record holder that once dominated every astronomy textbook, which modern telescopes have now dramatically downsized to a more modest 755 times the sun's breadth, completely shattering those early, exaggerated myths about its endless boundaries. When you zoom out and look at the universe's ultimate heavyweights, our colossal target remains an undisputed titan among giants. It truly rules an empire of one. However, the cosmos rarely gives up its secrets without throwing a massive curveball our way. Trying to slap a cosmic tape measure around these far-off, bloated monstrosities is a headache-inducing challenge for astrophysicists. These elderly stars constantly burp out immense, choking smog clouds of soot and heavy elements, essentially hiding themselves in their own cosmic pollution. This swirling debris field warps and blocks the outgoing starlight, creating a frustrating optical illusion that completely blurs the line between empty space and the actual edge of the star. On top of that visual trickery, these dying behemoths literally breathe, swelling up and shrinking down like a giant irregular lung over the span of months or even decades. Their physical boundaries are forever shifting, meaning the legendary Stephenson 218 you look at today could be wildly different in size tomorrow, continuing its eternal, mysterious dance in the dark. Have you ever wondered if our cosmic measurements are absolute? The truth is, every data point we collect is just a fleeting glimpse captured in time, carrying its own margin of uncertainty. When we say this giant spans 2,000 to 2,400 times the width of our Sun, we are looking at a rough ballpark estimate, rather than a hard and fast mathematical rule. As our telescopic technology advances in the coming years, astronomers will undoubtedly sharpen that blurry picture. We might even stumble upon an entirely new stellar behemoth hiding in the dark that dwarfs this current record holder. Alternatively, sharper lenses might reveal that Stephenson 218 is not quite the undisputed king we imagine it to be today. Yet, working with the absolute best astronomical evidence we currently possess, this colossal sphere reigns supreme as the undisputed heavyweight champion. But what kind of chaotic neighborhood gives birth to such a monster? Let us journey into the stellar nursery it calls home. Stephenson 2 operates as a sprawling open cluster, essentially a massive cosmic family of stars that all ignited from the exact same swirling cloud of interstellar gas. On the grand universal timeline, this neighborhood is practically a newborn, clocking in at a mere 20 million years of age. Yet, it hosts a staggering collection of the Milky Way's heaviest hitters, packed with an array of blazing red supergiants and ultra-massive hypergiants. Because this stellar family sits perfectly aligned with the main disk of our galaxy, it remains deeply buried inside a thick, hazy pocket of intense cosmic creation. All around this stellar family, the explosive process of birthing new suns is still blazing away at full throttle. Picture a chaotic environment, overflowing with thick cosmic dust and volatile gases, serving as the ultimate construction yard for celestial bodies. Astronomers widely consider Stephenson 2 to be among the heaviest and most densely packed stellar nurseries our galaxy has ever produced. To put that into perspective, the sheer weight of all its luminous residents combined tips the scales at roughly 50,000 to 100,000 times the mass of our own sun. Exploring further into this massive crowd, we find fascinating neighbors like Stephenson 2-3, which itself is a fiercely burning red hypergiant of unimaginable proportions, alongside Stephenson 2-7, an equally terrifying red supergiant, both representing colossal fireballs rapidly approaching the bitter end of their cosmic lifespans. Fast forward just a few million trips around the galactic center, and a vast majority of these heavyweights will detonate in blindingly catastrophic supernova blasts. Those violent shock waves, combined with chaotic gravitational tugs of war, will ultimately shred this once tight-knit neighborhood entirely. Open stellar groups like Stephenson 2 are inherently doomed to a very brief existence on the cosmic stage. Give it several tens of millions of years, and these blazing siblings will slowly wander away from one another, dissolving seamlessly into the vast, glittering ocean of the Milky Way. Therefore, the spectacular stellar congregation we are pointing our telescopes at right now is nothing more than a fleeting mirage. Think of it as a rare cosmic photograph, capturing a split second in universal history where a handful of colossal titans just happen to share the exact same zip code. Look ahead 100 million years into the future, and the entity we call Stephenson 2 will have completely vanished from the night sky. Every last one of its brilliant members will be hopelessly scattered across light years of empty, uncharted galactic real estate. However, the profound impact of these giants will echo through eternity. Through their apocalyptic destruction, they will aggressively seed the empty void with incredibly rare, heavy materials. Vital ingredients like carbon, life-giving oxygen, nitrogen, rigid silicon, solid iron, and a plethora of exotic metals are forged deep inside their bellies and unleashed violently during their explosive deaths. Out of that radioactive debris, entirely fresh, nutrient-dense nebulas will eventually take shape. Over eons, gravity will compress those rich, dusty veils down until brand new complex solar systems ignite in the darkness. Consider the microscopic building blocks making up your very flesh right now, or that metallic tang of iron pulsing through your veins, the sturdy calcium fortifying your skeleton, and every single breath of oxygen keeping you alive was originally cooked up inside the heart of an ancient, dying star. In fact, an overwhelming majority of those crucial life elements originated in colossal furnaces exactly like Stephenson 218, acting as the ultimate heavy machinery of cosmic manufacturing. These infernos are the sacred laboratories where the entire foundation of complex chemistry is actually forged. If these oversized giants never existed, our universe would be nothing more than a boring, empty void filled with nothing but simple hydrogen and helium gas. We would have absolutely zero solid planetary worlds to stand on, not a single drop of liquid water, and undoubtedly, a complete absence of biological existence. So while titans like Stephenson 218 are incredibly tough to find, they hold the absolute master key to creating any kind of chemical diversity in the cosmos. These fiery beasts burn through their fuel at terrifying speeds, guaranteeing a shockingly brief lifespan. Yet their violent final moments become the spectacular delivery system for the very puzzle pieces needed to construct tomorrow's habitable worlds. Which naturally brings us to an incredibly thought-provoking mystery. Could an alien civilization actually thrive on a world circling a terrifying behemoth like Stephenson 218? To put it bluntly, absolutely not. Any biological system attempting to survive near that kind of raging inferno would be completely impossible by our current understanding of science. Have you ever wondered why we do not search for alien worlds around the biggest stars in the cosmos? For starters, their lifespans are just a brief cosmic blink. Think about our own home. It took billions of years for the recipe of biology to truly cook up and thrive on our blue marble. The most basic, microscopic critters only showed up around 3.8 billion years in the past. And the complicated stuff, multi-celled creatures, stayed waiting in the wings until roughly 600 million years ago. Smart beings like us? A total flash in the pan. Meanwhile, a stellar behemoth like Stephenson 218 will burn out completely in a mere 20 million years. That is barely a ticking second on the cosmic clock. Nowhere near enough time for dead chemicals to spark into anything breathing. Then there is the sheer violence of the neighborhood. The space around these titans is an absolute nightmare. Imagine, against all astronomical odds, a young rocky world taking shape before its parent sun ballooned into a monstrous giant. That is already a massive stretch, but even then, this doomed sphere would be continuously scorched by a relentless storm of energy. The star essentially breathes, swelling and shrinking, throwing out wildly chaotic bursts of blinding light. Fierce, stellar gales would rip away any protective sky in a heartbeat. And the exact moment that star bloated outward, it would swallow up every single planet unlucky enough to be sitting in the front row. Even those rocky spheres that originally parked themselves in the cozy, so-called Goldilocks zone would be instantly turned to ash and vaporized by the advancing wall of stellar fire. Furthermore, cosmic heavyweights like this pump out devastating torrents of extreme ultraviolet rays and deadly X-rays. This kind of high-energy barrage acts exactly like a cosmic shredder, tearing apart the very chemical bonds that make complex life-building recipes utterly impossible to sustain on any neighboring rock. The single shred of hope for a livable planet here would involve parking it incredibly far out, dozens of astronomical units into the freezing dark, totally safe from the monster's bloated outer layers. Yet, even at that extreme distance, the brutal radioactive wash and the star's fleeting lifespan would crush any hopes of biology taking root. So the cold, hard truth? Orbiting a hypergiant is arguably the worst possible real estate for hunting extraterrestrial life. Biology, according to everything we currently comprehend, demands a peaceful, predictable sanctuary over epic timescales. It craves a sun that acts like a steady furnace, warming it dependably for eons. You absolutely must have flowing water, the right organic building blocks, and a solid cosmic shield against deadly rays. These colossal stellar giants fail miserably on every single one of those crucial requirements. Sure, they are breathtakingly gorgeous engines that heavily drive the chemical recycling of the entire cosmos, but they are absolutely nobody's home. If we want to find neighbors, we need to focus on stars exactly like our own sun, medium-sized, reliable engines burning quietly for billions of years, dishing out a perfectly even heat through entire geological eras. Or perhaps we peek around red dwarfs, the pint-sized campfires of the galaxy, which can keep glowing steadily for literally trillions of years. Granted, those little guys come with their own nasty baggage, like violent solar eruptions and worlds forever locked with one face to the fire. These massive stars are undeniably mesmerizing, but think of them as heavy industry plants rather than gentle nurseries. They forge the raw materials to build biology, but they outright refuse to nurture it. But let us flip the script and ask an entirely different, mind-bending question. What if an ultra-advanced intelligence decided to leash a beast like Stephenson 218 and steal all of its raw power. Enter the brilliant concept of the Dyson sphere, a colossal theoretical shell designed to trap a sun's entire output, dreamed up by the legendary physicist Freeman Dyson back in 1960. The vision paints a picture of a godlike alien race constructing a dense cloud of mirrored solar catchers, swarming around their host star to drink up a massive chunk of its blinding brilliance. Wrapping our own little sun like this would unleash a tidal wave of wattage, infinitely dwarfing the energy humanity consumes today. But scaling that up to Stephenson 218, the sheer voltage would break your brain. Keep this mind-blowing fact in focus. This Titan blasts out 440,000 times more power than our own daytime star. If you could siphon off merely a drop of that roaring ocean of light, you would wield an almost magical level of cosmic authority. Yet, practically speaking, trying to construct a megastructure around a hypergiant like this is a beautifully doomed engineering nightmare for a handful of wild reasons. To begin with, why bet on a cosmic giant that is already living on borrowed time? Long before you could ever finish assembling such a colossal piece of alien engineering, the stellar beast inside would already be knocking on death's door. Imagine pouring an unfathomable amount of raw materials and sweat into a galactic masterpiece, only to have it survive a measly few million years before a cataclysmic shockwave obliterates your hard work in an instant. Then, we must confront the sheer terrifying issue of scale. This flaming behemoth is so mind-bogglingly huge that finding enough physical matter to cage it is practically impossible. Constructing an unbroken sphere around a fiery core stretching 2 billion miles across would drain absolutely every rock and asteroid we have in our neighborhood. And it still would not be enough. An ambitious alien workforce would literally have to rip apart thousands of neighboring solar systems just to harvest the necessary building blocks. Finally, trying to work near this raging monster means battling ferocious cosmic storms and lethal heat, turning basic daily upkeep into a suicide mission. Whatever mega-shell you manage to erect would get relentlessly hammered by a brutal, non-stop hurricane of gamma rays and blistering atomic shrapnel. Surviving that environment demands a miraculous, ultra-tough armor that completely defies the laws of modern human engineering. So, where should a hyper-advanced society actually park their ultimate power plant? They would target a quiet, enduring campfire in the dark. Something familiar and welcoming like our own yellow sun, or perhaps a faint, slow-burning crimson dwarf. These modest furnaces will happily burn at a steady, gentle pace for billions of years, pumping out reliable electricity to fuel a galaxy-spanning empire from its dawn all the way into deep eternity. While a jaw-dropping hypergiant like Stephenson 218 might look like the ultimate prize, it is an absolute nightmare for sustainable power collection. It is simply a ticking time bomb, wildly erratic, violently angry, and destined for a very quick demise. But have you ever wondered what these raging titans actually do for the cosmos? Let us pan the camera back and witness their true purpose in the grand story of our universe. For more than 13 billion years, our swirling spiral home has been a relentless, glowing factory of light. Across those vast eons, an unmeasurable family tree of suns has flared to life, danced through the dark, and eventually faded into the abyss. The primordial ancestors of the cosmos, a legendary group known as the Third Population, were forged out of nothing but pristine hydrogen gas and raw helium. At that dawn of time, complex chemistry was a myth, because nature's forge had not yet started cooking the heavier ingredients. Those ancient pioneers were absolute titans, roaring with blinding intensity and burning through their fuel supplies so fast that they detonated as spectacular fireballs in merely a few million years. When they finally blew apart, they acted like cosmic dandelions, scattering the very first exotic materials across the empty void. Suddenly, the dark canvas was painted with the building blocks of life: carbon, oxygen, nitrogen, silicon, magnesium, and iron. This fresh cosmic dust churned together with the leftover primordial gases, brewing up vast, sparkling nebulas rich with potential. From these seasoned nursery clouds emerged the second wave of stellar children, carrying the legacy of their explosive ancestors. Though they only held a tiny pinch of those exotic ashes, it was exactly the spark needed to kickstart mysterious new chemical reactions in the swirling disks around them. Fast forward to our own familiar backyard, and we find our bright yellow star, a proud member of the youngest, most highly evolved lineage in the galactic neighborhood. Igniting around 4.6 billion years in the past, it pulled itself together from a rich cosmic soup, deeply fertilized by the spectacular deaths of countless ancient giants. Everything orbiting this modern star, including the very blue marble we call home, crystallized out of a swirling debris field where roughly 2% of the total weight was made of these complex, heavier building blocks. Every single atom of that precious 2% was forged in the fiery bellies of long-dead stellar ghosts. This brings us right back to modern-day behemoths like Stephenson 218. They are the active engines keeping this beautiful, violent recycling program alive. The moment this bloated giant finally shatters, it will vomit a treasure trove of freshly minted elements deep into the frigid spaces between worlds. Someday, far into the future, those drifting ashes will clump together to sculpt entirely new alien suns and perhaps undiscovered rocky shores. Through this endless rhythm of death and rebirth, our sprawling galaxy slowly marinates, growing thicker and richer with exotic materials. In the quirky language of astrophysicists, literally anything heavier than basic helium gets labeled a metal, completely tossing normal Earth chemistry out the window. So whenever you hear a space scientist geek out about a star being heavily metallic, they are simply marveling at how packed it is with all those wonderful, complex ashes from the stellar ancestors that came before it. Have you ever wondered why we consider certain glittering suns to be cosmic newborns? It all comes down to a heavy metal birth certificate, proving they materialized from the recycled ashes of countless ancient predecessors. Conversely, those celestial bodies lacking these complex ingredients are the true, weathered grandparents of the dark void. Born during the absolute dawn of time, they coalesced from pristine, untouched clouds. This brings us to a spectacular stellar toddler known as Stephenson 218, bursting with these rich, heavy alloys. Its birthplace was a chaotic galactic nursery, deeply seeded with an extraordinary abundance of exotic materials that were entirely forged within the fiery pressurized furnaces of long-dead stellar ancestors. Eventually, this bloated giant will meet its own explosive doom, detonating to fertilize the cosmic soil with an even richer blend of ingredients. It acts as a vital, blazing engine, driving our Milky Way's relentless march toward ultimate chemical complexity. Without this grand cycle of stellar recycling, intricate wonders like planets, moons, and life itself simply could not exist. The dawn of creation handed us a rather boring menu, consisting merely of hydrogen, a splash of helium, and a tiny dash of lithium. Yet every single carbon building block forming your DNA, every single molecule of the fresh air filling your lungs right now, and every microscopic speck of iron stabilizing the molten heart of our world, originated deep inside a burning stellar core. The vast majority of these life-giving building blocks were synthesized by colossal titans just like Stephenson 218, acting as the ultimate magicians of deep space. By crushing the most basic atomic ingredients under unimaginable gravity, they cook up the vibrant, intricate periodic table we know today. Their lifespans are mere fleeting blips on the cosmic clock, yet they burn with astonishing ferocity, ultimately shattering to enrich the boundless void. If these massive foundries never ignited, our reality would remain an endlessly dark, barren, and utterly monotonous wasteland. So how do we actually peek inside these distant, roaring foundries? Unlocking the closely guarded secrets of a colossal behemoth like Stephenson 218 requires some serious scientific ingenuity. We obviously cannot just hail a cosmic cab or launch a robotic envoy to knock on its front door. Sitting 19,000 light-years deep into the abyss, a theoretical ship riding a photon beam would still take 19,000 years just to arrive. Absolutely nothing constructed by human hands possesses the capability to bridge that terrifying chasm. Consider Voyager 1, the swiftest and most remote mechanical scout humanity has ever launched. Despite zooming through the dark for greater than 47 years, it has barely scratched the surface, crawling a microscopic 0.002 light-years. Cruising at that agonizingly sluggish pace, an intercept course with Stephenson 218 would require millions of lifetimes, forcing us to play celestial detective from our own backyard using mammoth lenses. Astronomers act as grand light catchers, trapping the faint stellar glow, fracturing it into a stunning rainbow barcode and decoding the hidden messages within. Think of it like a cosmic fingerprint, where every distinct chemical ingredient leaves a unique signature of color by either soaking up or radiating specific energy waves. Scanning these energetic barcodes to spot missing or prominent bands empowers us to reconstruct the exact recipe of the sun's fiery atmosphere. It simultaneously reveals the beast's blazing heat, the terrifying speed at which it races through the dark, and a myriad of other hidden physical traits. Additionally, scientists keep a watchful eye on its glowing intensity, tracking how the illumination ebbs and flows across the calendar. A significant number of these crimson gargantuans are notorious shapeshifters in the night sky. This means their radiant output flickers in a steady rhythm, driven by violent, throbbing heartbeats deep within their plasma layers. Imagine a massive lung inhaling and exhaling. The stellar surface swells and shrinks, dramatically altering its thermal footprint and its overall glow. Charting these dramatic physical tremors grants us unparalleled insight into the internal architecture and chaotic mechanics governing the giant. While optical observatories capture what human eyes can comprehend, the real magic frequently relies on heat-sensing, invisible technologies. You see, Stephenson 218 is notoriously camera-shy, hiding behind a colossal, suffocating veil of cosmic smog. This murky curtain consists of local soot swirling right next to the giant, plus vast stretches of shadowy debris drifting through the enormous gulf separating our worlds. Fortunately, thermal radiation operates like galactic X-ray vision, slicing effortlessly through these thick, muddy stellar clouds. This specialized trick pulls back the galactic curtain, though tuning our giant antennas to catch invisible electromagnetic static provides yet another vital puzzle piece. Sizzling gas spheres naturally broadcast faint frequency hums, and listening to these whispers unveils the secrets of howling plasma gales, invisible force fields, and bizarre energetic eruptions. Then there is a brilliant astronomical trick known as interferometry. By networking several distant dishes together to digitally mimic one Earth-sized superlens, scientists can unlock breathtakingly crisp cosmic visuals. Pioneering researchers have already utilized this exact synchronized wizardry to literally trace the physical outlines of several bloated stellar neighbors residing right in our solar backyard. But when aiming our sights at an ultra-remote leviathan like Stephenson 218, pulling off this synchronized trick becomes a Herculean nightmare, demanding impossibly wide telescope arrays, which is why we largely depend on light intensity tracking and barcode scanning to uncover its secrets. After all, simply gauging the raw luminous intensity of these beacons provides our clearest window into the grand cosmic theater. By breaking down this light into its core colors, a technique known as spectroscopy, astronomers unlock a staggeringly detailed profile of these celestial giants. Suddenly, its searing heat, blinding brightness, chemical makeup, colossal weight, sheer size, lifespan, and current life stage are laid bare before us. And the wildest part? We figure all of this out just by catching ancient beams of light that have been racing across 19,000 light-years of the cosmic void. It is a profound tribute to the sheer brilliance of the human mind and the unwavering laws of physics, allowing us to intimately know a distant world our species will never actually touch. But let me ask you this: out of everything out there, how many cosmic leviathans like Stephenson 218 are actually hiding in our home galaxy? The truth is, hardly any at all. These stellar beasts, known as hypergiants, are the ultimate cosmic unicorns. Even though the Milky Way is swirling with hundreds of billions of fiery stars, astronomers have managed to track down a mere handful, just a few dozen of these absolute titans. Why so few? Well, it is a mix of them being incredibly scarce by nature, combined with the fact that they are notoriously brilliant at playing cosmic hide-and-seek. They are constantly cloaked behind thick, swirling curtains of interstellar dust, buried deep within incredibly remote or densely packed neighborhoods of space, and on cosmic timescales, they burn out in the blink of an eye. Let us say our galaxy births one of these monsters every couple of thousand years. Even then, their turbulent lives are over in just a few million years. Because of this furious burn rate, at any exact moment in time, you are looking at perhaps just a few thousand of them scattered across the entire sprawling expanse of our galaxy. Naturally, the vast majority of those remain heavily shrouded or pushed far beyond the reach of our current telescopes. The rare handful we have successfully unmasked are essentially our cosmic neighbors, sitting within a radius of just a few tens of thousands of light years. That makes Stephenson 218 positioned roughly 19,000 light years away. An absolute marvel. It is among the farthest of these giants we have ever managed to put under the microscope. Without a doubt, there are even more massive behemoths lurking further out in the dark, completely invisible behind walls of astronomical debris. It is highly likely that we will unearth more of these sleeping giants as our next-generation telescopes come online and map out wider stretches of the cosmos. Yet, by their very design, hypergiants will eternally remain an anomaly, a fleeting, chaotic chapter strictly reserved for the absolute heaviest stars in the universe. The vast majority of stars burning in the night sky will never even come close to reaching this colossal status. They simply lack the sheer gravitational bulk to ignite such an extreme transformation. To even stand a chance, a newborn star needs to tip the scales at roughly 20 to 25 times the mass of our own sun. And even with that staggering weight, everything has to align perfectly. More often than not, these heavyweights tear themselves apart in catastrophic supernova explosions while they are still incredibly hot blue supergiants. Only a select few survive long enough to bloat outward into red supergiants, and just a tiny sliver of those survivors mutate into the ultra-rare hypergiants. This brings us back to Stephenson 218, an unparalleled cosmic oddity, offering us a front-row seat to the most chaotic, absolute limits of a dying star's life cycle. It is a celestial body that has literally stretched the boundaries of physics until they almost snap. Now, let us circle back to that mind-bending picture we painted earlier. Picture yourself planted firmly on Earth, gazing up into the quiet, starlit canopy above. Now, mentally swap out our familiar, warming sun and drop the monstrous bulk of Stephenson 218 right into the dead center of our cosmic neighborhood. The heavens above you would become entirely unrecognizable. When dawn breaks, do not expect a piercing, golden sphere soaring above the horizon. Instead, an impossibly massive, ominously dim crimson wall would swallow up nearly the entire sky. Its terrifying outer edge would be looming so uncomfortably close that it completely drops the illusion of being a single dot of light, flattening out into a colossal dome. In fact, Because your vantage point is technically swallowed within the star's outermost atmospheric layers, everything around you would be choked with violently glowing superheated gases. Naturally, our beautiful blue marble could never actually survive this apocalyptic scenario. Long before the star reached this size, its ravenous expansion would have instantly boiled the oceans and incinerated the planet into nothingness. But if we suspend reality and imagine an indestructible viewing platform anchored exactly where Earth's orbit used to be, one astronomical unit away from the core, you would find yourself plunging unimaginably deep inside the raging belly of this stellar behemoth. The heat would blast past thousands of degrees, accompanied by crushing, inconceivable cosmic pressures. Swirling oceans of incandescent plasma would envelop your platform from every conceivable angle. Peering through the storm, the inferno would grow blindingly intense as your eyes track down toward the star's nuclear heart, fading only slightly into a dusky, turbulent haze where its distant surface struggles to hold together. There is no solid ground here, no clear edge where the star stops and the void of space begins. Just an endless, chaotic ocean of fire waiting to be explored. Imagine floating in an infinite ocean of radiant plasma, where gravity gives you absolutely zero sense of up or down. In a way, it is the ultimate cosmic inferno, an incredibly brutal environment that would instantly vaporize any biological life or solid matter. But paradoxically, this blazing furnace is also the ultimate cosmic factory. Deep within its belly, heavy atomic ingredients are actively being forged, cooking up the very same building blocks that will someday form solid worlds and breathing organisms. The exact same ferocious forces making this zone completely unlivable are actually what allow our cosmos to evolve past simple gas into something beautiful and complex. We are talking about nuclear fusion roaring in the center, massive boiling currents of plasma churning in the outer layers, and violent stellar gales ripping away matter. Ultimately, a colossal explosion will detonate, blasting these freshly baked ingredients across trillions of miles of empty space. You might think this sounds like pure devastation, but it is actually the ultimate act of creation. This violent alchemy is exactly how the cosmos manufactures the essential chemical scaffolding for everything we know and love. Make no mistake, Stephenson 218 is living on borrowed time. Sometime in the next couple of million years, or perhaps even sooner, this gargantuan beast is going to detonate. When that happens, humanity will have a front row seat. A brilliant, brand new beacon of light will suddenly flare up in the Scutum constellation. For weeks, maybe even months, it will burn so intensely that it will easily overpower almost every other celestial object in our night sky before eventually dimming away. The ghostly shell left behind by this blast will keep expanding outward, morphing into a spectacular nebula that could dazzle stargazers for thousands of years before it slowly dissolves into the dark void. All those precious elements cooked up inside the supergiant and forged during its fiery death will then blend seamlessly into the vast cosmic dust clouds. From those nutrient-rich clouds, a completely new generation of stars will ignite. Orbiting those fresh suns, entire new planetary systems will take shape. And perhaps on one of those rocky worlds, biological wonders will spark into existence. If they do, those creatures will literally owe their very heartbeat to the remnants of Stephenson 218. The carbon woven through their cellular structures, the breathable oxygen in their skies, and the molten iron warming their planet from the inside out. Every single atom will trace its origins back to titanic stellar factories just like this. This is the true poetic legacy of the universe's most massive stars. Their destiny is not to settle down as quiet, permanent fixtures in the galaxy. Instead, their purpose is to sacrifice themselves, scattering the cosmic fertilizer required to grow future wonders. As we wrap up our cosmic journey, pause for a moment and consider what a behemoth like Stephenson 218 actually teaches us about the cosmos. Simply put, a monstrous anomaly like this actively breaks the rules of everything we thought we knew about stellar physics. On paper, a celestial body of this sheer magnitude should instantly tear itself apart. Yet there it sits, burning brightly. The intense pressure generated by its own blinding radiation ought to shred its outer layers into confetti. Against all odds, gravity manages to keep the whole chaotic mess glued together, at least temporarily. By turning our telescopes toward these impossible giants, astrophysicists can upgrade their foundational theories. They act as the ultimate cosmic stress test, pushing our mathematical models to their absolute breaking points. Each time we catch a glimpse of one of these leviathans, we uncover crucial clues that help us crack the underlying code of universal mechanics. Still, we are essentially fumbling in the dark on several fronts. For instance, the exact mechanics of how these giants bleed away their mass remains a massive puzzle. What exactly is the trigger that causes a hypergiant to violently exhale billions of tons of its own atmosphere? Where is the hidden engine powering these ferocious solar gales? And just how much of itself does the star shed before the end? Furthermore, its deep internal anatomy is practically a total mystery to us. What kind of chaotic dance is taking place inside the core? How do boiling currents of plasma manage to cycle through an object that is incredibly massive, yet weirdly fluffy and spread out? Does it resemble a cosmic onion, wrapped in distinct layers of entirely different chemical elements? Most tantalizing of all, we have absolutely no idea how its story truly ends. Is Stephenson 218 destined for a standard issue supernova finale? Or are we going to witness a terrifyingly weird, unseen type of detonation? Is it possible it might just silently swallow itself whole, collapsing into a bottomless black hole without uttering a single visible flash? These mind-bending mysteries are still completely unsolved, and the singular path toward discovering the truth requires us to endlessly keep our eyes glued to the skies, construct even more powerful telescopes, and constantly rewrite the textbooks of astrophysics. Have you ever wondered what happens when the laws of physics are pushed to their absolute limits? Studying titans like Stephenson 218 helps astronomers crack that exact mystery. It is far from just another dot on a graph. This behemoth is the ultimate cosmic outlier. Grasping how these massive freaks of nature operate is the master key to unlocking the entire spectrum of celestial phenomena. If we spent all our time looking at average, quiet yellow dwarfs like our own sun, our understanding of the galaxy would be incredibly blind. To get the full story, we have to look everywhere, from the tiniest cosmic embers to the most colossal titans, from the blistering infernos to the freezing remnants, and from newborn protostars to ancient stellar ghosts. Every single variation holds a crucial puzzle piece. The sheer scale of hypergiants reveals our universe's absolute boundaries. Just how massive can a celestial body grow before it tears itself apart? How blindingly bright, how violently chaotic can it get before it completely implodes? What exactly takes place when gravity and nuclear fusion go to war at the edge of physical reality? Stephenson 218 holds the clues to those profound mysteries, even as it throws wild new puzzles our way for the future. So, grab a front row seat as we dive into the beautifully chaotic world of red hypergiants and discover what makes them so mesmerizing. These gargantuan beasts are caught in a blink-and-you-miss-it phase of their celestial lifespan. Imagine a heavyweight champion that has completely burned through its primary hydrogen fuel tank, leaving it no choice but to start forging heavier, denser elements deep within its fiery heart just to stay alive. Yet, the final, fatal explosion of a stellar supernova is still just waiting in the wings. This awkward cosmic puberty breeds some of the most bizarre and extreme physical environments imaginable. Deep inside, the star's engine is shrinking and baking at unimaginable temperatures, violently crushing helium down into carbon and oxygen. As that inner core collapses in on itself, it blasts immense waves of gravitational heat outward into the surrounding gas. Reacting to that intense flood of energy, the outer atmospheric layers balloon outward to mind-boggling proportions. It sounds completely backwards, but this is the beautiful paradox of astrophysics. A crushed, shrinking heart directly forces the outer shell to swell up like a gigantic hot air balloon. Because it stretches out across billions of miles of empty space, that outer envelope actually drops dramatically in temperature. While a prime-of-life heavyweight might scorch at tens of thousands of degrees, this bloated giant cools down to merely a few thousand, totally transforming its character and appearance. That chilling effect shifts the star's glowing signature away from a fierce, piercing blue and turns it into a deep, smoldering crimson. You might think a cooler surface means a weaker star, but the reality is exactly the opposite. The sheer brilliance skyrockets because there is simply so much more glowing real estate available to beam out light. Picture it like this. A tiny white-hot spark from a fireworks sparkler is incredibly intense, but it barely lights up your hand. Meanwhile, a gigantic glowing bonfire might have much cooler flames, yet it radiates enough total heat to warm an entire crowd. That is the exact same optical magic happening with these bloated red monsters. Every individual patch of its surface might be relatively chilly for a star, but multiply that by billions of miles of surface area, and the total blinding power is almost impossible to comprehend. Now, the most mind-bending part of this story is that these behemoths are constantly throwing tantrums. They are anything but calm. They violently heave, they throb, and their blinding light flickers wildly across the cosmos. Their gravitational grip on their own outer atmosphere is so incredibly weak that they constantly vomit their own mass out into the void. Ferocious gales of stellar wind rip away the star's flesh and carry it into the darkness. At a pace so chaotic, it would give any structural engineer absolute nightmares trying to calculate the stability. To put numbers to it, astronomers suspect Stephenson 218 throws away about 1/10,000th of our sun's entire weight every single year. In everyday terms, that tiny fraction might not sound like an earth-shattering loss, but let that cosmic clock run for 1,000,000 years, and you are looking at 100 entire suns ripped apart and scattered. Bleeding out this much physical material completely changes the star's ultimate fate and structure. Bit by bit, layer by layer, this colossal giant is physically shrinking down as it continuously sheds its own skin. All those violently discarded guts and debris do not just vanish. They hang around, choking the vacuum surrounding the dying star. It builds up into a massive, murky shroud, forming a dense fog of space dust and swirling gases that hides the beast within. So when we peer through our telescopes at Stephenson 218, we aren't just looking at a star. We are gazing through the hazy veil of a chaotic stellar graveyard. Have you ever tried looking at a distant light bulb through a thick cloud of smoke? That is exactly what we face here. We are not just observing the naked star, but also the dense cosmic fog wrapping around it. Nailing down exact numbers becomes a massive headache, as astronomers must separate the true starlight from the glowing halo of debris hiding it. What forces this shroud outward? The sheer power of the star's own light literally shoves the matter into deep space. Trillions of tiny light packets crash into individual atoms and specks of dust, physically ramming them further into the void. All those microscopic collisions add up to a tremendous outward force, generating a relentless stellar gale. Do not picture a gentle, continuous breeze, though. This cosmic storm is chaotic, spitting out violent, unpredictable clumps of debris. When we peer closely at these crimson behemoths, we notice something wild happening. Their outer layers are boiling with absolutely colossal convection bubbles. Plumes of scorching plasma surge upward, while cooler currents plunge back down, painting a picture much like a pot of roaring, boiling water on your stove. but scaled up to mind-bending proportions. Just one of these bubbling surface blobs could easily swallow our planet's entire journey around the sun. Because of this aggressive boiling, the face of the star gets painted with contrasting patches of intense heat and relative chill. Even though these titans spin at a sluggish pace, that rotation drags those mottled patches right across our line of sight. From our vantage point here at home, we witness those shifting spots as flickering changes in the star's overall glow. Decoding those flickers allows scientists to unlock secrets about how fast the giant spins, the strange geography of its outer skin, and how fluid dynamics work when pushed to absolute extremes. But what if the star is actually breathing? Another reason these giants flicker is that they physically pulse. Over spans ranging from a few months to several years, the entire stellar body balloons outward before shrinking back down. As it exhales and swells, the outer boundaries push into space, increasing the giant's sheer volume while causing its surface heat to dip slightly. When it inhales and shrinks, things heat back up. This rhythmic heartbeat is powered by a phenomenon known as the Kappa mechanism, a cosmic trap where the outer gas becomes thick and cloudy, capturing an immense amount of internal energy. That trapped energy causes the atmosphere to boil, swell dramatically, become transparent, cool off, and plummet backward. It is a perpetual cosmic rhythm, much like a stretched spring endlessly bouncing. Take the colossal Stephenson 218, for instance. Its massive heartbeat could alter its total size by 10 to 20% in just a year or two. That translates to the giant morphing anywhere from 1,800 to 2,200 times the width of our sun during a single cycle. Tracking this heavy breathing grants scientists a rare window into the beast's hidden, deep architecture, since the rhythm of the pulse is directly tied to the total weight, overall size, and the way matter is packed away deep within its core. But what about the unseen forces? Let us venture into the realm of stellar magnetism. Nearly all luminous spheres in the cosmos host magnetic webs, forged by the violent churning of dynamos buried in their hearts. Our own local star uses its magnetic power to sculpt dark blemishes, unleash fiery flares, and hurl massive bursts of plasma toward us. These crimson superbeasts undoubtedly possess their own magnetic networks, yet detecting them is incredibly tough since these titans lurk so incredibly far away from our telescopes. Inside one of these swollen monsters, the magnetic landscape is constantly twisted by its spin and the violent boiling of its outer skin. Whenever those massive bubbles of plasma heave upward and crash back down, they pull the invisible magnetic threads along for the ride, weaving a remarkably chaotic, tangled web of forces. They could act like invisible cosmic highways, funneling raw stellar matter outward into the void, much like how our own sun guides the fierce solar gale through our planetary neighborhood. Furthermore, twisted magnetic threads can bunch up and trap immense energy, roasting very specific patches of the upper atmosphere to extreme temperatures. Those hyperheated zones are likely the culprits behind the mysterious beams of X-ray light that our satellites have caught radiating from some of these crimson giants. Finding high-energy X-rays streaming out of a relatively freezing stellar giant might sound completely absurd. Have you ever wondered how something freezing could harbor pockets of unimaginable fire? Well, intense magnetic forces can whip up localized patches of scorching, superheated gas, even within the frigid outer layers of a dying star. Untangling the magnetic mysteries of these crimson behemoths is actually one of the hottest frontiers in modern astrophysics. Thanks to next-generation observatory tech, especially specialized tools that read the twisted light signatures left by magnetic waves, scientists are finally charting out these invisible forces. Every single piece of data we gather pulls back the curtain a little more on how these monstrous cosmic engines actually tick. But to truly wrap your mind around this level of sheer vastness, we need to bring things a bit closer to home. Picture this. The distance from the core to the edge of Stephenson, 218 spans, roughly 930 million miles. Let us translate that monstrous figure into a scale that makes a little more sense. In the realm of cosmic yardsticks, we are talking about exactly 10 astronomical units. Keep in mind, a single astronomical unit is the entire gap between our home planet and the Sun, sitting right around 93 million miles. So the distance from this Titan's core to its edge alone stretches out to 23 times the span between Earth and our local star. This means the total width across this beast measures a staggering 20 astronomical units. Think about the frosty edges of our neighborhood, where Neptune reigns as the most distant true planet, circling at 30 astronomical units out. If you somehow dragged Stephenson 218 and dropped it right where our Sun sits, its burning outer shell would push so far out into the darkness that it would surpass the outer gas giants. Even our beloved dwarf planet Pluto, which hangs out at an average of 39 astronomical units away, would be completely consumed within the blazing belly of this colossal sphere. What about the Kuiper Belt? That massive ring of frozen debris floating in the dark. It begins at 30 and stretches all the way to 50 astronomical units from the center. Those icy remnants would just barely escape destruction, lingering safely beyond the hypergiant's fiery reach. Only the celestial bodies caught within that initial 10 astronomical unit danger zone would be instantly vaporized. Now, let us shift our perspective to the flow of time. A photon races through the vacuum at a blistering 186,000 miles per second. At that velocity, you could wrap a beam of light around Earth's equator 7.5 times in a single heartbeat. It only needs 8 minutes and 20 seconds to make the entire journey from the Sun's surface to your backyard. But what happens when we ask that same lightning-fast beam to traverse the width of Stephenson 218? You have an expanse of 1,860,000,000 miles, pitted against a speed limit of 186,000 miles per second. Do the math, and that ultimate speedster needs a full 10,000 seconds just to get from one side to the other. That breaks down to nearly 2 hours and 47 minutes of non-stop travel. Picture that. Almost 3 hours for the fastest thing in existence, just to travel from one edge of this star to the opposite side. For perspective, a photon zips across our Sun's width in a mere 4.66 seconds and flashes across Earth in an imperceptible 0.042 seconds. We are dealing with an object so inconceivably huge that light itself, the ultimate speed champion of reality, requires upwards of 6 hours to traverse it. Imagine floating right in the star's core and flashing a laser pointer toward the outer edge. That distress signal would be traveling for 1 hour and 24 minutes before it ever broke through the surface. And in that time frame, the chaotic, boiling atmosphere above would have completely rearranged itself. But wait. What about its sheer weight? Earlier, we established that Stephenson 218 packs roughly 12 to 16 times the total material of our Sun. Our local star weighs in at roughly 2 times 10 to the 30th power kilograms, literally a 2 trailing behind 30 zeros. To put that in perspective, that is roughly 330,000 times heavier than the planet you are standing on right now. Crunch those numbers, and this hypergiant holds somewhere between 24 and 32 times 10 to the 30th power kilograms of matter. You are looking at the gravitational equivalent of stuffing anywhere from 4 million to 5,300,000 Earths onto a cosmic scale. Here is the mind-bending twist, though. All of that weight is stretched across a spatial footprint 10 billion times more expansive than our Sun, meaning its overall density is actually a billion times thinner. Have you ever wondered what happens when a cosmic behemoth outgrows our own solar anchor? Our Sun sits at an average density of roughly 1.4 grams per cubic centimeter, making it just a fraction denser than ordinary water. But when we look at the colossal titan known as Stephenson 218, the math gets absolutely staggering, dropping to an average density of 0.00014 grams per cubic centimeter. To put that into perspective, we are talking about a mere 14 millionths of a single gram occupying an entire cubic centimeter of space. Let's visualize that. The absolute most perfect, empty vacuum scientists can possibly engineer right here on Earth holds about 1/1,000,000th of a gram in that exact same volume. So while this stellar giant technically contains thousands of times more matter than our emptiest artificial environments, it exists as essentially a cosmic ghost, shockingly diffuse and airy compared to any normal star. Deep within its heart, however, gravity paints a completely different picture. The stellar engine burning inside likely rivals or even vastly surpasses the crushing pressures found at the center of our own sun. Yet its sprawling outer layers are little more than a whisper of gas, a vast, ethereal cloud that would feel like an absolute void to human senses. How did we even begin to comprehend these magnificent cosmic monsters? To answer that, we have to rewind the clock. For thousands of years, our ancestors gazed up at the night sky and assumed those twinkling lights were permanent, immortal fixtures of the cosmos. Classical Greek philosophers labeled them the unchanging heavens, deliberately separating them from the restless, celestial wanderers we now know as planets. The universe kept its secrets hidden until the Renaissance, when sharp-eyed stargazers finally noticed the sky was actually alive and evolving. The grand illusion shattered in the year 1572. The legendary astronomer Tycho Brahe spotted a sudden brilliant beacon blazing to life within the familiar shape of Cassiopeia. This unexpected visitor outshone even the planet Venus, burning so fiercely it could be seen perfectly clearly in broad daylight. What he was witnessing was the explosive death of a star, a spectacular supernova, though humanity wouldn't invent that word for hundreds of years. Then in 1604, the brilliant Johannes Kepler caught sight of yet another stellar detonation, this time in the constellation of Ophiuchus. These violent cosmic displays completely dismantled the ancient myth of a peaceful, static universe. Still, the true identity of these glowing orbs remained one of humanity's greatest unsolved puzzles. Could they be distant relatives of our own sun, burning far out in the void? Or were they entirely alien celestial bodies hanging at unimaginable distances? The shadows of ignorance wouldn't lift until the scientific revolutions of the 19th and 20th centuries illuminated the dark. Around the mid-1800s, a magical new tool called spectroscopy was born, giving scientists the power to essentially read the hidden messages carried by starlight. By catching a beam of illumination and fracturing it into a vibrant rainbow, researchers unlocked the ability to see the exact chemical ingredients floating within a distant star's atmosphere. It turns out that every single element interacts with light in a unique way, absorbing and radiating energy at very specific frequencies. This cosmic dance leaves behind undeniable chemical fingerprints buried inside the light. Reading these light signatures unveiled a startling truth. The heavens are predominantly forged from hydrogen and helium, the exact same building blocks we have here at home, just mixed in radically different cosmic recipes. But the light held another secret, proving that these distant furnaces burn at wildly different heat levels. The most scorching giants glow with a fierce azure hue, while the cooler bodies smolder in deep crimson. Fast forward to the early 1900s, when visionary scientists Egnar Hertzsprung and Henry Norris Russell each sketched out a groundbreaking map of the cosmos, forever known as the Hertzsprung-Russell diagram. Think of it as a master blueprint of the universe, directly comparing how blindingly bright a star is against how intensely hot it burns. Scatter thousands of starry data points across this chart, and breathtaking cosmic families suddenly reveal themselves. The vast majority of our glowing neighbors neatly organize themselves along a sweeping diagonal line. Astronomers call this bustling neighborhood the main sequence, and it is exactly where our cozy, familiar sun resides. Yet, venture off this well-trodden path, and you will find the rebels of the universe, Meet the staggering giants and supergiants, cosmic anomalies that pump out exponentially more blinding light than ordinary stars burning at the exact same temperature. Drifting up into the top right territory of our cosmic map, we encounter the looming red giants and supergiants. These beautiful anomalies are blindingly brilliant, yet strangely, their surface temperatures are relatively frigid. As our stargazing technology evolved, and we mapped millions of new celestial bodies, scientists realized this crimson corner of the chart stretched upward into realms of unimaginable, eye-watering brilliance. A rare few shine with such ferocious intensity that they completely outclass and overshadow absolutely everything in their galactic neighborhood. Ultimately, humanity had to invent an entirely new title for these breathtakingly bright, chillingly cool monsters: the legendary hypergiants. Have you ever wondered what happens when a star gets so absurdly massive that scientists have to invent a whole new word just for it? Enter the hypergiant. These stellar monsters aren't merely stepping up a size class. They exist entirely on their own mind-bending level of extreme physics. Back in the 1930s, stargazers spotted early titans like VV Cephei, which turned out to be a crimson behemoth boasting a mind-boggling waistline. Then there was Mu Cephei, beautifully nicknamed Herschel's Garnet Star due to its rich ruby glow, marking another classic heavyweight from our early cosmic catalogs. For decades, the undisputed king of the cosmos was believed to be VY Canis Majoris, with 1990s data hinting it could swallow 2,800 of our suns edge to edge. However, sharper modern tech eventually shrank that waistline down to around 1,420 times our sun's width. That is still a jaw-dropping scale, though definitely a downgrade from its mythical initial hype. Honestly, this kind of cosmic downsizing happens all the time in astrophysics. Whenever our telescopic lenses get sharper and our analytical tricks get smarter, we naturally dial in on the absolute truth of these celestial giants. Those fuzzy older photographs basically forced researchers to guess, meaning the raw facts frequently end up looking wildly different from the rough drafts. Take UY Scuti, a fierce heavyweight challenger first noticed back in the 1860s. We completely misunderstood its epic proportions until modern heat-sensing cameras finally pierced through the galactic fog to reveal the truth. Early calculations hyped up this fiery beast to have a staggering girth, approaching 1,900 solar radii. Yet today's ultra-precise scans place it much closer to a modest 755 solar widths. Then, the ultimate plot twist arrived with Stephenson 218, hiding in a star cluster only mapped back in 1990. But zooming in to weigh the individual sparkling diamonds inside that cluster took quite a bit longer. We had to wait until the 2000s and 2010s for next-level thermal imaging to finally unlock the secrets and true dimensions of the fiery spheres clustered inside. Out of that cosmic crowd, Stephenson 218 suddenly stepped up as the undeniable frontrunner for the undisputed biggest sun we have ever laid eyes on. Thanks to an incredibly bloated profile and rock-solid modern data backing it up, this beast currently reigns at the absolute peak of the heavyweight chart. But the universe is a vast arena, and this cosmic heavyweight title bout is far from over. Unlocking deep space is a relentless, never-ending detective story. Fresh glowing orbs get spotted, dusty math gets corrected, and the leaderboard constantly reshuffles. Right now, we can confidently declare that Stephenson 218 is an absolute titan among the stellar population, holding a very real claim to the ultimate crown. As we launch better gear into the void, our grip on these mind-bending realities will only grow tighter. So how exactly do we even look at something sitting that far out in the dark? Peering at Stephenson 218 isn't a job for your backyard telescope. You need heavy-duty, customized hardware. Standard glass lenses are practically blind here, completely choked out by incredibly thick clouds of cosmic soot. This monster hides out directly within the flat, pancake-like middle of our Milky Way, which acts as a gigantic dumping ground for the vast majority of our galaxy's floating debris. Imagine trying to look through a raging blizzard. That is exactly how much cosmic junk is wedged between Earth and this star. This floating smog acts like a massive filter, eagerly swallowing up shorter wavelengths like blues and greens, while letting the longer crimson waves slip past. It is the exact reason why certain patches of your nighttime view look mysteriously pitch black. Have you ever noticed how the glowing stripe of our home galaxy is broken up by shadowy, inky rivers? Those aren't empty spaces. They are ultra-dense fog banks entirely blacking out the brilliant neighborhood of suns sitting just behind them. To slice right through that visual wall, scientists have to swap out normal cameras for powerful thermal imaging tech. Because heat radiation stretches out much further than colors we can see, it simply glides past the debris without bumping into anything. The very same microscopic soot particles that completely blind. Our naked eyes are basically invisible glass to an infrared lens, pulling back the curtain on the universe's greatest secrets. Have you ever wondered how we actually see the invisible monsters lurking in the dark corners of our galaxy? Well, a whole fleet of incredible infrared eyes in the sky has spent years uncovering the secrets of the colossal star Stephenson 218. Let us rewind to 1983, when a pioneering machine called the Infrared Astronomical Satellite roared into the blackness of space. This magnificent piece of technology acted as one of humanity's very first sets of thermal goggles orbiting our world. It swept its mechanical gaze across the entire cosmic canvas, looking at the heat radiating from hidden celestial objects. Think of it like a cosmic heat detector that spotted hundreds of thousands of glowing hotspots, revealing a hidden realm of chilly, dust-shrouded stellar giants. Thanks to that early heat map, astronomers first flagged the Stephenson 2 stellar family as a prime target for future cosmic detective work. Fast forward to the late 1990s and the dawn of the new millennium, when the 2-micron all-sky survey stepped onto the scene. This ambitious project meticulously painted a fresh portrait of the heavens using near-infrared light, peeling back the cosmic curtain even further. It handed scientists a much sharper map, pinpointing the exact locations and blazing intensities of the celestial bodies huddled within that distant grouping. With this upgraded view, researchers could finally begin untangling that crowded stellar neighborhood, isolating specific stars like picking out individual glowing embers in a roaring campfire. Then came a true game-changer for astronomy: the legendary Spitzer Space Telescope. Blasting off in 2003, this marvel delivered unbelievably crisp thermal snapshots and dazzling light signatures. Spitzer was like a deep-sea diver for the cosmos, capable of sensing much longer waves of heat energy than its predecessors ever could. This superpower allowed it to peer right through thick cosmic fog, revealing freezing dust clouds and unlocking visually impenetrable stellar nurseries. These deep dives were critical for mapping the vast, smoky halos surrounding titanic objects like Stephenson 218. Not to be outdone, the Herschel Space Observatory soon joined the grand cosmic quest. Scanning the heavens from 2009 until 2013, it pushed our vision into the extreme realms of far infrared and sub-millimeter light. Herschel was the ultimate ice hunter, perfectly tuned to trace the most frigid gas and dust veils drifting around these monstrous suns. But we do not just rely on orbiting robots. Giant mechanical eyes bolted right here on Earth have been just as essential in solving these deep space mysteries. Take the appropriately named Very Large Telescope, perched high in the Chilean mountains. Managed by the European Southern Observatory, this beast is armed with an impressive arsenal of cutting-edge, heat-sensing gadgets. It boasts massive light-gathering mirrors, perfectly situated in the desolate Atacama Desert. Because that barren landscape is basically completely stripped of moisture, it blocks far less starlight than anywhere else on the planet. This ultimate dry zone makes it an absolute paradise for thermal astronomy, while the twin Keck giants perched on a Hawaiian volcano serve as heavy hitters in both visible and heat-seeking observations. These monolithic structures have also locked their sights onto the blazing behemoths dwelling within the Stephenson 2 family. To fight the blur of our planet's atmosphere, these ground-based titans wield a magical technology known as adaptive optics. Imagine putting on a pair of smart glasses that instantly undistorts a funhouse mirror. That is exactly how this system smooths out the twinkling night sky on the fly. The secret behind this incredible trick lies in a highly flexible, shape-shifting component. It uses a specialized mirror that literally warps and bends its own surface hundreds of times every single second to cancel out the visual static. It perfectly counteracts the chaotic bubbling and boiling of the Earth's gaseous blanket. As a result, our Earth-bound observatories can capture photographs so breathtakingly crisp you would swear they were snapped by a satellite deep in the vacuum of space. This wizardry works exceptionally well when tracking heat waves, since thermal light cuts through our turbulent air much easier than regular visible light does. But snapping pretty pictures is only half the battle. To truly decode a star's DNA, we rely on the mind-bending science of spectroscopy. Think of it like passing sunlight through a prism to create a rainbow. Scientists shatter the stellar glow into a barcode of specific glowing and dark bands. By reading this cosmic barcode, space detectives can instantly figure out the deepest secrets hidden inside a star. It reveals everything: how blisteringly hot the surface is, what chemical ingredients it is made of, and exactly how fast it is rocketing through the void. The ultimate tools for this job are high-definition spectrographs. These incredible devices slice the light so finely that they catch the tiny shadows cast by completely distinct chemicals and compounds floating in the star's atmosphere. Those missing slivers of light are the smoking gun, proving beyond a doubt exactly which elements are bubbling away in the stellar furnace. When we decode the light from Stephenson 218, the chemical fingerprints scream that its outer layers are laced with surprising things like titanium oxide and actual water vapor. Now, compounds like these are incredibly fragile and would instantly be incinerated on an average star. The fact that they survive at all proves this absolute monster is freezing cold by astronomical standards, cementing its title as a rare red hypergiant. But the magic of reading light does not stop at chemistry. It also acts like a cosmic radar gun. We can track exactly how rapidly the star is plunging toward us or fleeing away by watching its light stretch or compress in a phenomenon called the Doppler effect. Just like an ambulance siren pitches up as it rushes in your direction, a star charging at our solar system will literally squash its light waves, shifting its entire glow toward the blue end of the rainbow. Think of it like a cosmic siren approaching us. The light waves bunch up, becoming just a tiny bit shorter than normal. But what if our stellar giant is speeding away into the dark? That light gets stretched out, taking on a reddish hue. Those elongated waves act like a galactic radar gun, letting us calculate exactly how fast the object is traveling. And that brings us back to our colossal friend, Stephenson 218. By tracking its precise speed along our line of sight, astronomers can actually prove it belongs to the Stephenson 2 stellar family. After all, a true star cluster drifts through the vastness of space together, like a cosmic flock of birds sharing the exact same trajectory. Then there is the fascinating art of capturing starlight. By carefully watching how a star's glow strengthens and fades over the years, we can uncover its hidden heartbeat. Robotic eyes on Earth gaze up night after night, sweeping across the heavens without rest. They paint a sweeping portrait of light, charting exactly how erratic behemoths like Stephenson 218 flicker in the dark. These glowing charts are basically cosmic EKGs, showing us the exact rhythm and intensity of the star's throbbing surface. Is this giant breathing in a steady, calming rhythm? Or is it gasping wildly and unpredictably? Exactly how violent are these flashes? Answering these questions let scientists peek beneath the stellar hood to understand its turbulent internal engine. But how do we see the unseeable? Enter a brilliant trick called interferometry. This method links several separate observatories together, creating a virtual superlens far sharper than any lone mirror ever built. By perfectly synchronizing the tiny ripples of starlight as they strike different dishes around the globe, researchers can mathematically piece together breathtaking pictures. It essentially mimics a mammoth telescope as wide as the actual physical gap between the connected facilities. Take the incredibly powerful Very Large Telescope Array in the Chilean desert. This network has successfully mapped the sheer width of massive red giants lingering in our local cosmic neighborhood. When you blend those precise visual angles with how far away the star is, you finally get its true, terrifying physical proportions. However, when dealing with remote monsters like Stephenson 218, this clever trick hits a wall. The star is so unfathomably distant that it appears as nothing more than an infinitely tiny speck. Yet, there is hope on the horizon. Tomorrow's massive telescope networks, stretched across even vaster distances, might just snap a direct picture. That breakthrough would finally hand us the exact tape measure needed for this Titan's waistline. It would wipe away the hazy guesswork that clouds our current understanding of its true scale. So what happens when time finally runs out for a bloated hypergiant? The universe gets treated to one of its most violent fireworks displays. A Type II supernova. This specific catastrophe triggers when the heart of a heavyweight star utterly gives out under its own gravity. Picture it like this. For millions of years, the stellar core has been a nuclear forge, crushing lighter atoms into incredibly dense new materials. It burns hydrogen into helium, then forces helium to become carbon and oxygen, moving all the way up the elemental ladder to neon and magnesium. But there is a catch. Every new fusion phase burns hotter, vanishes quicker, and yields terribly diminishing returns of energy. Ultimately, the desperate star starts melting silicon down into heavy iron. This agonizing final gasp lasts barely a handful of days, because iron acts as the ultimate cosmic ash. Trying to squeeze iron into anything heavier does not generate any outward pushing power at all. Instead, it greedily absorbs energy, instantly killing the fusion engine the moment the core turns to solid iron. Now, the only thing keeping the star from crushing itself is a bizarre quantum shield known as electron degeneracy pressure. It is a strict rule of the microscopic world that outright forbids tiny subatomic electrons from occupying the exact same space at the exact same time. But even the laws of quantum mechanics have their breaking point against raw gravity, a threshold known as the Chandrasekhar limit. For a dead iron heart, that snapping point is roughly 1.4 times the mass of our own sun. The instant it packs on just a fraction more weight, those quantum pillars instantly shatter and fail. The center falls out of the star in a truly terrifying freefall. In a fraction of a single heartbeat, less than 1 second, a solid metallic core the size of Earth is violently crushed into a sphere no larger than 20 meters wide. Have you ever wondered what happens when gravity completely breaks the laws of physics, crushing matter until it perfectly mimics the heart of an atom, becoming 100 trillion times thicker than a simple glass of water? Under this incomprehensible weight, the very building blocks of reality surrender as negative and positive particles violently smash together to forge neutral ones, throwing off ghostly bursts of neutrinos in the process. What remains is a bizarre celestial corpse known as a neutron star, a sphere so impossibly packed that just a single spoonful scooped from its surface would weigh a staggering 1 billion tons here on Earth. This catastrophic implosion happens in the blink of an eye, completely blinding the upper atmosphere of the giant star to the disaster unfolding far below. Those massive outer envelopes are basically plunging into a void, completely unaware that the dead center has suddenly hit maximum capacity, slamming the brakes on its own freefall. Like a cosmic ocean slamming into an impenetrable brick wall, Millions of miles of infalling stellar gas violently crash against this hardened center and rebound furiously. This dramatic ricochet births an unstoppable wave of kinetic force, ripping its way back up toward the surface of the dying sun, carrying unimaginable fury. This outward surge superheats the star's upper atmosphere to billions of degrees, sparking a sudden and violent chain reaction where entirely new atomic cores are rapidly forged. You see, everyday stellar ovens cannot bake anything heavier than iron, so the universe relies on this exact apocalyptic blast to manufacture the heavyweights of the periodic table. The shimmering gold in your jewelry, the shiny platinum, the heavy uranium, and countless other complex metals are born purely out of the chaotic inferno of this split-second stellar death. Tearing the dying sun apart, the blast throws its shredded remains across the cosmos at blistering speeds ranging from 10,000 to 30,000 meters per second. All that shattered stardust blooms outward like a magnificent ghostly bubble, forming what astronomers call a supernova remnant. This spectacular wreckage paints the darkness with brilliant light as the sheer force of the shockwave sets the surrounding cosmic winds ablaze. If we looked up from our own backyards, this catastrophic event would masquerade as a brilliant new beacon, suddenly glowing within the scutum star pattern. Out of nowhere, it would pierce the dark canvas of the night sky, potentially shining at a visual magnitude of -7 or -8, which completely outshines Venus and allows it to be clearly seen even under the glaring midday sun. This celestial fireworks display would dominate the heavens for several weeks before slowly vanishing into the abyss over the course of many months. If a scientist were to chart the intensity of this flash on a graph, they would notice an intense, immediate spike the moment the shock wave punches through the star's outer skin, cresting precisely when the debris cloud reaches its absolute hottest, followed by a long, slow dimming phase as the gas bubble inflates, chills, and turns completely see-through. Interestingly, the only thing keeping the lights on during this fading period is the slow, steady breakdown of highly unstable radioactive metals born during the blast, mostly a specific type of nickel known as nickel-56, which slowly morphs into cobalt-56 and ultimately settles down as iron-56. The phantom heat radiating from this subatomic shapeshifting acts as an invisible battery, pumping out just enough juice to keep the stellar graveyard illuminated for months after the original detonation. But here is the wildest part. Those ghostly neutrinos we mentioned earlier actually steal away a staggering 99% of the explosion's total power. Because these phantom particles can effortlessly slice right through solid matter without leaving a trace, they flee the scene of the crime instantly, rushing away from the dead heart of the star at practically the absolute speed limit of the universe. That means a measly 1% of the actual force goes into creating the spectacular light show we see through our telescopes. Yet, even that tiny fraction holds a level of sheer destruction that defies human comprehension. An average core collapse event will unleash an unfathomable 10 to the 46 joules of energy, flooding the cosmos with blinding radiation and ferocious motion. To put that into perspective, it is roughly 100 times the total amount of energy our own sun will manage to produce over its entire 10 billion-year lifespan, all unleashed in a matter of heartbeats. The shock wave would violently fling the equivalent of 10 to 15 entire suns worth of raw churning matter out into the freezing void. Packed with all those freshly minted heavy metals from the star's lifetime and its explosive death, this rich cosmic fertilizer would drift out to mingle with the vast, empty oceans of deep space. After drifting endlessly for millions of years, the scattered stardust would gradually chill and gather together, sweeping up into majestic, swirling nurseries of dark gas and ice. Deep inside these shadowy nebulas, gravity takes hold once again, pulling the dust together to birth an entirely new generation of burning suns. And the beautiful truth is, these young suns would be packed with an even greater variety of heavy elements than their massive ancestor, Stephenson 218. This majestic cycle of cosmic recycling keeps moving forward, slowly peppering the universe with the ingredients for life, exactly as it has since the dawn of time. Meanwhile, sitting quietly in the center of the wreckage, the ultra-dense core, either a shadowy black hole or a neutron star, would stubbornly linger in the dark. Should that remnant happen to be a neutron star, we might catch it winking at us across the galaxy as a pulsar, acting as a frenzied cosmic lighthouse that spins wildly out of control, sweeping the darkness with blinding, rhythmic beams of intense radiation. Picture a cosmic lighthouse violently spinning in the dark, sweeping brilliant searchlights across the void. Whenever that searchlight happens to flash directly across our little blue world, our telescopes catch a steady rhythm of radio signals, which is exactly why we call them pulsars. These dead stars whip around at mind-bending speeds, with some completing hundreds of full rotations every single second. Imagine crushing a mountain down to the size of a sugar cube, then wrapping it in a magnetic grip trillions of times more powerful than the pull of our own planet. We are literally looking at some of the most brutal and untamed environments in the entire cosmos, providing scientists with the ultimate playground to test the laws of nature under. Bizarre extremes that would be utterly impossible to ever fake in an earthbound lab. But what happens when the dying heart of a star is just too heavy, completely overwhelming the outward push of its own nuclear particles? Gravity wins the ultimate tug of war, crushing the remnant straight down into the infinite abyss of a black hole. If a monstrous giant like Stephenson 218 ever met this fate, the resulting dark void would pack the heft of 10 to 15 of our suns. Yet the point of no return, the shadowy event horizon, would span a mere 60 to 90 miles in diameter. That is a speck of dust compared to its former glorious size. Yet it traps the entire gravitational might of the original stellar core. These ghost stars rarely dance alone. We usually spot these collapsed titans locked in a gravitational waltz with a living partner star. Should that fiery companion wander too close, the invisible predator begins siphoning off its atmosphere, wrapping itself in a glowing, swirling whirlpool of stolen gas, as this captured stellar debris spirals relentlessly toward the center. Friction sparks unimaginable heat, boiling the plasma to millions of degrees and screaming out intense flashes of X-ray light. In fact, these vampiric celestial pairings light up our telescopes as the most blinding X-ray beacons scattered across the Milky Way. The blazing halo of doomed plasma effectively gives away their hiding spots, making them far easier to hunt down than their solitary cousins. A lone singularity wandering the void is perfectly invisible, swallowing every drop of light that hits it. Finding them is practically a cosmic game of hide and seek, only won when they accidentally drift across our view of a distant star, bending and magnifying that background glow through the sheer warp of gravity. But what about the outer layers blasted away during the star's death? That shock wave of stellar shrapnel bursts outward at thousands of miles per second. Given a few millennia, this beautiful explosion swells into a cosmic bubble stretching dozens of light years from end to end. As eons pass, the phantom clouds stretch too thin, losing their fiery glow as the cosmic ashes settle and freeze. You might already know some of these spectacular celestial graveyards, like the breathtaking Crab Nebula, born from a stellar detonation that lit up Earth's skies in the year 1054. Today, its neon-colored tendrils are kept energized by a furious central pulsar, whipping around 30 times a second and injecting massive electrical surges straight into the surrounding gas. Then there is Cassiopeia A, the wreckage of another colossal explosion that tore through space near the year 1680. Interestingly, stargazers back then totally missed the fireworks, as thick curtains of cosmic smog completely block the flash. These expanding debris clouds act like giant open-air classrooms, letting astronomers untangle the chaotic physics of stellar death, track supersonic blast waves, and watch how dead star guts smash into the freezing emptiness of the galaxy. Someday, the shattered remains of Stephenson 218 will carve its own legendary painting in the night sky. It is destined to morph into a sprawling radioactive bubble of heavy metals, shining bright in radio and X-ray frequencies before fading into the vast galactic ocean. But before we move on, there is one fascinating puzzle piece we have to talk about. The colossal smog machines operating around these dying giants. Monsters like red hypergiants are permanently cloaked in a dense fog, built up from millions of years of forcefully coughing their own outer atmospheres into space. These cosmic soot particles are born the moment the stellar breeze travels far enough away, plummeting in temperature until vaporized elements lock together into tiny solid crystals. If you venture too close to the stellar surface, the blistering inferno absolutely vaporizes any attempt at forming solid matter. In that chaotic zone, gas is stripped bare into glowing plasma and atomic bonds shatter instantly. But step back into the cooler void, and magic happens. Once the thermometer drops down to just a few thousand degrees, chemistry takes over, forging the building blocks of liquid water, toxic carbon monoxide, and exotic titanium oxides. Drift further still into the shadows, where the heat drains away completely, and an extraordinary physical transformation kicks into high gear. Out in the deep chill, the floating gas finally hardens into tangible, rocky shrapnel. We are talking microscopic flakes of iron, dark carbon soot, and rocky silicates, all perfectly forged, depending on the exact recipe of the local space weather. Though individually microscopic, have you ever wondered what cloaks the most colossal giants in our galaxy? We are talking about cosmic particles so unimaginably tiny, measuring just fractions of a single micron, dwarfing even the finest speck of beach sand. Yet when these microscopic specks group together, they build colossal dense fogs capable of completely masking the glowing heart of the celestial body from our normal vision. Think of this material as a giant sponge that eagerly soaks up all the standard visual and ultraviolet illumination pouring out of the stellar giant, cooking the cloud from the inside out until it fiercely glows with invisible thermal energy. That magical transformation is exactly the reason these soot-covered behemoths shine like brilliant beacons when viewed through thermal imaging cameras. While they might look like faint ghosts to our naked human eyes, their raw power never disappeared. It merely transformed into stretched-out thermal waves. Picture a hurricane of pure illumination, where the sheer force of starlight physically shoves this soot further out into the dark void. Trillions of tiny light packets slam into every piece of debris, acting like microscopic battering rams that continuously knock the material away. When dealing with the tiniest flecks of matter, this relentless barrage of light actually becomes stronger than the crushing pull of gravity, forcefully ejecting the material into deep space. Imagine these speeding soot particles acting like snowplows, crashing into surrounding gaseous clouds and carrying that atmospheric material right along for the ride. What we get is a massive, dirty cosmic gale, an endless river of vapor and debris pouring away from the central furnace. This aggressive breeze literally blows the giant apart, ripping off its fluffy outer atmosphere piece by piece. As the centuries roll by, this continuous shedding forces the stellar giant to bleed away a massive chunk of its original bulk. Take the gargantuan monster Stephenson 218, for instance, where this surrounding soot blanket stretches outward for countless times the width of the giant itself. We are talking about a halo so huge, it could swallow up dozens, perhaps even hundreds of distances equivalent to the space between our Earth and the Sun.